Thank you for downloading this podcast from The Reedy Clubby Show on Talk Radio 702 and 567 Cape Talk. For more, please go to 702.co.za or capetalk.co.za.
Some respect the property of others. What are you doing to lead us a?
The Naked Scientist on Talk Radio 702 and 567 Cape Talk with Reedy Clubby.
28 minutes to 10 o'clock and the Naked Scientist is here, not here in the studio. Now I'm going to have hordes of people just rushing to Prime Media in Sandton. He's not here. He's in the UK, but chatting to us. Our lines are open on 021 446 0567 011 883 0702. Chris, good morning.
Good morning.
Lovely to chat to you. I'm fascinated by this. We always talk about this on the show, malaria and how people can protect themselves. There's new research which has revealed some fascinating information. Tell us about it.
Yes, indeed, Reedy. It's official. Malaria gives mosquitoes the munchies, and specifically a taste for humans. There's a paper in PLOS One this week. It's by a researcher called James Logan and his colleagues. He's based at the London School of Hygiene and Tropical Medicine, and they have discovered that when mosquitoes, and specifically Anopheles mosquitoes that spread malaria, are infected with the parasite, they become much more attracted and are much more prone to bite the smell of a person. When I say the smell of a person, this is because they've done the experiment using sheets of nylon membrane, one of which was impregnated with the odours of a person's skin, the other wasn't, and initially they did the experiment with uninfected mosquitoes, and they counted over a period of time how many mosquitoes landed on each piece of pseudo skin, and predictably, because we know mosquitoes are drawn to the smell of people, there were far more landing and biting events on the piece of human-smelling nylon compared with the piece of nylon that was unimpregnated. But then they repeated the experiment with mosquitoes that were now malaria-infected, and the numbers that were landing on the piece of nylon that smells like a human were 4 times higher. Now, the researchers don't know exactly why the mosquitoes make a beeline, if that's the right word, for the human smelling piece of nylon, but they suspect that the parasite is in some way manipulating the ability of the mosquito to respond to smell. The mosquito does this using its antennae, and it could be that the parasite increases the number of receptors or the sensitivity of the receptors on the antennae for those smells, making it want to go and bite another person when it is highly infectious, which is beneficial to the parasite because it would pass on the malaria much more efficiently and increase the numbers of cases in the population.
Very interesting indeed. And Chris, we spoke about this on the show yesterday, that actually psychiatrists at Cambridge University have started a study of the adolescent brain, which they aim to pinpoint, in which they aim to pinpoint changes in the way the adolescent brain is wired. Do you know anything about that? But just generally a conversation about our brains and how they reflect the different stages of our lives.
Well, as we grow up, your brain responds to the changes in the world around you, your daily experiences, and you learn new things, you remember things, you interact with people, and all of these things change the connections in your brain between one nerve cell and another. And obviously the time when this is happening at an enormously fast pace is during your adolescent phase, because you're not only grappling with learning about the world around you, you're also developing very quickly, you're going through puberty, there are lots of hormones circulating which are changing the way different bits of your body work and look, and that includes your brain too. And so a very dramatic change in our behaviour switches between pre-adolescence and when we've gone through puberty. So therefore the brain must be altering its connections, it must be altering the relative importance of different parts of the brain and producing different behaviour patterns that we see in an adult compared to the sorts of patterns of behaviour that we see in children. And in particular, we're interested in the opposite sex usually, and we spend enormous amounts of money after that pursuing the opposite and sometimes the same sex. So how does this happen? What changes happen in the brain to bring about these changes? Why is it that when we're adolescent we're much better at we're much worse at reading the feelings of other people, but when we're a mature adult or a young child, we're much better at perceiving other people's feelings. Researchers now want to understand how the brain is changing and rewiring itself during this important phase, and they're doing all kinds of studies now, including what we call longitudinal studies, where you follow an individual for a long period of time, over many years, and you do repeated brain scans, for example, or repeated psychometric tests to see how different parts of the brain are altering their activity. And this will help us to build a picture of how the brain develops, and that will be good for people who are developing normally, but it also means we'll become better at spotting people who might be developing differently, and that means we might be in a position to help people that might be destined to develop a problem down the line, some kind of mental illness or learning difficulty. We can anticipate when they're going off the track a bit and maybe develop some interventions to help them get back on the right track.
All right, and Chris, I understand you received an email about bubbles. I've never actually paid attention to the colour of bubbles. They just see-through and transparent, but are they white?
Yes, there was a tweet at the end of last week's programme, and that tweet to @NakedScientist, if anyone wants to tweet me, it's lovely to hear from you. The question was a good one, and it was, why is it that when I buy bubble bath or bubble foam, it comes in all kinds of beautiful colours, but when you then make the bubbles, they always look a white colour? And better still, if you look at the bubbles, there's a sort of rainbow colour reflected in them. Why don't you get pink or red or blue bubbles? And the reason for this is that the bubble foam itself does contain colorants, chemicals that reflect certain colours or wavelengths of light to give the bubble bath or the bubble foam its colour when it's in the bottle. But when you make a bubble, the bubble film is so thin, and we know it's extremely thin, it's in fact so thin it's almost as thin as the wavelength of light. That means that there's not enough space in the bubble film for very much, if any, of that colorant to collect. And therefore, when you look through the bubble film, it's effectively transparent. But why do the bubbles as a mass look white? It's the same reason that water is transparent, but when you look at snow, it looks white, because when you've got lots of little particles all together, when light goes into a new medium, a new substance out of the air, it changes its speed a little bit, and this causes it to bend. So when light comes out of the air and goes into a whole load of ice, or snow, then it goes into the water, bends a bit, it goes into another bit of water, bends a bit, goes into another bit of water, bends a bit. This has the effect of reflecting back at you all of the different colours or wavelengths of light, and if you add all of the colours together, you see a white colour, which is why snow looks white, and bubble bath is doing exactly the same thing, and so is milk, actually. There are lots of tiny blobs of fat floating around in milk and proteins, and those have the same effect, and they bend all of the light round and reflect it back at you, and it looks a white colour.
Our lines are open for you. Give us a call on 021 446 0567, 011 883 0702, and your SMSs as well on 31702 and 31567. What do you want to ask the Naked Scientist? Sean in Fourways. Good morning.
Good morning. How are you?
Good.
Good, man. My question is, if you had to take a person, a human being, and put them in a sealed container with adequate oxygen supply, if you weigh the container and then have the person exercise for an hour, and you weigh the container afterwards, would there be a weight loss?
Hello, Sean. The container is sealed, and therefore all of the mass, the particles that are in there, all of the atoms, because if you think about it, all you've done is to put a whole bunch of atoms in that box. The atoms just happen to be arranged into molecules that resemble a person and gas molecules. If that's sealed, then the person can only use or break down or rearrange the atoms that are in the box, and that means that there will be no addition or loss of atoms from the box, and since the mass of what is in the box comes from the atoms, therefore there won't be any significant mass change. And I use that word cautiously because there is a small effect, which is that if you move, because of E equals mc squared, if you're taking potential energy away from chemicals to rearrange them, so you have some sugar which you break down to make your energy, you will rearrange the molecules into some carbon dioxide which you'll breathe out, but there will be less chemical potential energy in the molecule because carbon dioxide is more stable than the sugar it came from, and so there will be a tiny amount of mass loss owing to Einstein's equation, but on the whole, unless you were measuring it extremely, extremely precisely and with enormous accuracy, you wouldn't see any difference in the mass.
Thank you very much, Sean. And how do I say your name? Pipa?
P-Pacific.
P-Pacific.
Yes.
Okay. Good morning to you. Welcome.
Thank you. Thanks, Rudy. I want to ask the naked scientist, when a spaceship is on Earth, it pushes against the ground when it burns fuel. And then it goes in the atmosphere, it pushes against the air. When it gets in the outer space, what does it push against if there is no air there? How does it move forward and how does it turn around?
Okay, let me see if I've got this right. So, P Pacifique, is that right?
Yes.
Brilliant.
Good,
okay,
Chris.
well, good question. Okay, so when the space rocket is taking off from the Earth, it isn't actually pushing on the ground. That's a myth, perhaps, conception. What's happening is that the space rocket is burning fuel. Usually it is hydrogen and oxygen. And you mix those two things together and you get a violent explosion and a lot of heat. And this causes the gas, the water vapour that's made to expand. And the shape of the rocket means that it all won't fit in the rocket thruster, so it has to go outwards. And it's thrown by the rocket backwards. And Isaac Newton discovered and put this into a series of laws, the laws of motion, that for every action there's an equal and opposite reaction. So if the water vapour that's produced and goes gunning out of the back of the rocket is pushed away from the rocket, it must give a push on the rocket back the other way, equal and opposite to the force that was applied to the gas that was leaving the rocket. So it doesn't actually matter whether the rocket's on Earth, in orbit, or in deep space. It's throwing gas out of the back of the rocket, and that gas is giving a push back in the opposite direction on the rocket. It's not actually pushing on anything.
Okay.
Oh, interesting.
Is that
I understand.
Thank you very much, P Pacific.
Pleasure.
Thank you for calling us
Bye-bye.
from Mondio. Very interesting name. Never heard it before. But anyway, stay on the line, please, Kwabena. And I've got your SMSs as well. We're taking a break and we'll be back with more of your questions for Chris.
The Naked Scientist on Talk Radio 702 and 567 Cape Talk with Rudy Clappy.
Our lines are open for you on 021 446 0567 011 883 0702. Is it Kwabena in Klipspruit?
Yes, hi.
Hi.
I'm just curious, like when you turn off the hot water faucet, it starts with cold water for like a few seconds and then it goes to hot. I have no idea why that happens.
Hello, Gwabena. So the reason for this is that the hot water that's coming down the pipe is coming from the hot water tank. The hot water tank has got a heater in it, usually the geyser, or the boiler supplying it, but the pipe, which goes from the tank to your tap, is usually uninsulated and has no source of heat of its own, so it can only lose heat. So if the water's been standing in the pipe for any period of time, it will have lost energy, thermal energy, just by radiation and conduction along the pipe and so on. And the result of that will be that the water will be cooler. And depending upon how long it's been sitting in the pipe, the water will be more or less cool. And when you open the tap, you empty the pipe of the cooler water before it's replaced by the hotter stuff from the tank.
All right, Kwabena,
Thanks.
does that answer?
Yeah,
Thank you
thank
very
you.
much. Chris, what's the latest on the random, the reality of random numbers? Do we have any new information?
Aha! Do you know what I've got in front of me right now? I have got a wonderful answer. I'll just give you a little niblet from this.
Good enough for allowing a computer to simulate rolling a dice, flipping a...
I've got the audio,
Yes.
and I've just published this. So if you go to nakedscientist.com, this is a very kind piece of audio written by Evan Stan. It's been put together by a guy called Evan Stanbury, actually. He lives in Australia. Listen to us there. So he listened to the problem, and he has recorded for us a 5-minute answer to this. A bit too long to play in this show. So what I've done is turned it into its own podcast and put it on the front of The Naked Scientist. So if you go to nakedscientist.com, you'll see there's a thing on the front page there that says, "What is random?" And you can download that piece and listen to his answer. He explains what is a random number, how do computers generate random numbers. They're not really random numbers, and he explains why, and goes into all the details on it.
Okay, Chris, I'll tell you what. I'm being outvoted here. My producers want to hear it. So does Thomas. They want to hear the entire clip.
Ooh, it's 5 minutes. Are you sure?
Are you guys sure? They are.
They are. I'll play it for you. Are you ready, everybody?
Yes, we are.
Okay, here we go.
When we think of random numbers, we often think of something like rolling dice, flipping a coin, or shuffling a deck of cards. Random numbers add a degree of interest to games because every game is then different. Variation makes computer-generated art more realistic and computer-generated voices more natural. Random numbers are also useful in simulating the complex events of the real world in Monte Carlo simulations, named after the famous casino in Monaco. Another application is for encryption. When you do a transaction on your bank account, you don't want anyone else monitoring it. These are all things that we want to do on a computer these days. Typically, a computer rolls a virtual dice with 1 billion or more sides, which can be considered as a number between 1 and 1 billion, or, more commonly, a number between 0 and 1. We can then use formulas to translate this into another type of random number, like drawing the next card from a deck, which we might represent as a number between 1 and 52. To generate truly random numbers, you need a non-predictable hardware circuit, like measuring the voltage of a Zener diode that generates random noise, quantum effects like the rate of radioactive decay, or recording the instance in time that somebody types a character on a computer keyboard, or using an unstable circuit like a ring oscillator. Perhaps surprisingly, it's often difficult to get enough randomness from sources like this, so we use computer programs called pseudo-random number generators to produce an indefinite supply of numbers that look random enough for our purposes. Computer pioneer John von Neumann said, "Anyone who considers arithmetic methods of producing random digits is, of course, in a state of sin." Using predictable circuits such as we have in a computer always produces a predictable result, if you know the program and the inputs to the program. But this is quite good enough for allowing a computer to simulate rolling a dice, flipping a coin, doing computer animation, or creating a model of the motion of stars in our galaxy. Most computer languages have a built-in random number generator, which is purely software. This depends on having a random seed as a starting point, and then repeatedly applying a program which modifies this to produce a new number, which looks quite different from the previous number. A good random number generator won't generate the same sequence of numbers for a very long time. One popular method takes a starting number and uses just one multiplication, one addition, and one division to produce another number which looks quite different from the first one. By applying the same equation over and over again, you can generate a sequence of numbers which looks quite random, unless you happen to know the starting number and the equation, and then it becomes entirely predictable. To prove that a number is quite random, well, think of a dice. If the dice is fair, all of the numbers from 1 to 6 will come up, and roughly as often as each other. For a computerized random number generator, mathematicians apply an exhaustive series of tests, like the following. We know that numbers from a computer will eventually repeat, but how long does it take to repeat? It should be as long as possible. Do all of the numbers from 1 to 1 billion come up? If a particular number comes up again, is it always followed by the same number? There are statistical tests to verify that all the numbers come up approximately the same number of times, but not exactly the same number of times, because that wouldn't be random. You expect to find numbers getting larger or smaller with equal probability. And if you take a single bit of the number, it's a 1 or a 0, like flipping a coin. Now, some bits of the random number generator may not be as random as some other bits. The random numbers may appear random if you look at every number, but are they still random if you look at every third number or every 12th number? Probably the most demanding application of pseudo-random numbers is encryption, because a hostile person may be willing to spend a lot of money and computer time on cracking the code and trying as many seeds as possible. For this reason, the US and German governments have published rules listing the actual tests that must be passed if a random number generator is to be used for various purposes. Some new computer chips have hardware to generate genuinely random numbers, and this is built in, which will help them generate an unlimited supply of random numbers to make our modern computerized lives just a little bit more interesting.
Now, there's the power of listener input. Thank you very much to Evan Stanbury, who did that for us. Isn't that amazing?
Delightful. Absolutely delightful. Zendo in Benoni, hi.
Hi, I'd like to ask the naked scientist how many. I'm building a rocket. So how many grams to a square centimeter of parachute? Could you tell me a formula or?
Oh, that's a really good question, and I don't know, because obviously it's going to be different according to what sort of material it's passing through. Because if you're going to send your rocket to, say, Mars, where the atmosphere is really thin, you're going to need a much bigger parachute to slow it down, because there's not much for the parachute to get hold of, compared with on Earth, where the atmosphere's what we have, or Titan, where the atmosphere is really, really, really thick. Now, I'm going to presume you're going to send the rocket just up into Earth atmosphere at the moment, because this is just a prototype, and I don't actually know the formula. What I would tend to do is do an experiment, and do a standardized experiment where you make a parachute, and you put a known mass onto the parachute, and drop it from a certain height, and see how fast it's going when it hits the ground, or track how long it takes to go from the drop to the ground, which will enable you to work out how much a certain mass will fall in proportion to the size of the parachute. Because as the mass gets bigger, then the downward force accelerating it under gravity is going to get bigger, so you're going to need a bigger and bigger parachute. But it should follow a pretty standard straight line if you do a series of different masses that you test, and then you should be able to extrapolate to how big you need it to get your rocket down safely. But I will look and see if there is actually any formula for you, and I'll come back to you next week. But I would, for now, so you don't hold up your rocket engineering designs, I would do the simple experiment with a range of different masses and see how the speed of the descent changes according to the different mass and the size of the parachute.
All right, Zendo, what we'll do is we're going to take your number, and then we're going to phone you, and if the naked scientist has an answer for us next week, we'll put you up so that you can hear the answer for yourself. Chris, thank you so much for a lovely show and all the effort you put into answering all our questions. I particularly loved the random numbers one, and we're getting great feedback.
Okay.
Thank you, most appreciated.
If anyone missed that, actually, it is now on the front page of the Naked Scientist website. It says, what is random? So if you go to nakedscientist.com, you can see what is random, and there's a link there to either play that again or download it if anyone wants to grab it again or refer it to someone else. And thanks once again to Evan for sending us that. That's the power of citizens journalism, I think they call it, isn't it?
We love it. And of course, we will podcast the program so they can get it there as well. Have a lovely weekend, Chris.
Thanks, Reedy.
Ta-ta.
Bye-bye, everybody.